Hello everyone, welcome to my JuliaCon 2021 talk on Dictionaries.jl. Okay, I'm going to break this talk into three sections. First we're going to talk about what is this, why on earth did I do this? We'll look into the inside and how it works internally, and we'll go to the REPL and we'll look at some applications. We'll see how it's used in practice. So what is it that we've created? I've created this package called Dictionaries.jl that basically introduces an alternative interface for dictionaries. So there's an abstract dictionary supertype to replace abstract dict, and an abstract indices supertype which you could use in place of abstract set. Okay, and there's two concrete types which I'll talk about here, but there's others, and it's easy to implement your own concrete types. Dictionary and indices, which are a bit like dict and set. Okay, these are just hash dictionaries. Now they behave very much similar to what's in base, but there are some slight differences. Okay, and we'll go through what's different, and we'll go through what's better. Well, what I believe is better. Okay, so firstly, we should start with really saying that the dictionaries and sets in base are actually really good. They're well implemented. They're fast. There's actually lots of useful functionality, and you know, if you compare it to any other programming language, they're really great. Okay, but Julia's array capabilities are out of this world good. You know, Julia's arrays, they're powerful, expressive, they're fastest handwritten C code. Okay, so the idea here is attempt to bring some of this real magical capabilities that we have with arrays and bring them over to dictionaries. Okay, so that we can be a bit more productive and have better performance for analytics workloads. So how does this work? So fundamentally, there's this little thought experiment I like to do, which is, you know, if you think of an array is a container where if you give it an index, it will give you a value. It's a kind of dictionary, you know. So what if there was some kind of supertype which encompassed both dictionaries and arrays? What would that supertype look like? Okay, what would it look like? So you know, this supertype, it should let us do all these things that I love to do with arrays. I love to do broadcasting, filtering, sorting. We can slice and dice our data. We can reduce over all our data or subsets of data. You know, flattening. We can do lazy operations. There's lots of lazy operations built in that we can opt into. And you can use vectors as stacks and queues and heaps and things. So that there's tons of things you can do with Julia just by using base and vector and vectors of vectors and things like that. Okay. And you know, sometimes I have data which is naturally it's indexed. It behaves like a set, or it behaves like a dictionary. And I'd love to do all these things with those containers, but unfortunately, we don't get a lot of this behavior out of the box. You have to implement it yourself, or some of them you can use ordered collections.jl, and you get some of this functionality back, which is great. But what we're going to do here is we're going to see, you know, if we just make a few tweaks between arrays and dictionaries, we can actually define all of these things. Okay. So if you're doing data modeling, you're picking up a new problem and you want to model your data, you're always going to use arrays, sets, and dictionaries. They're the core data modeling structures. You see them again and again in every programming language. That's what we use, you know, in our heads. It's what we use in our JSON and that kind of thing. Okay, so the idea here is to create a single interface which is cohesive across arrays, dictionaries, and sets. And the two things we're going to tie together is that for these things, indexing and iteration, they're going to be tied together in a special way. Okay, it's not a pretty obvious way, in fact. So arrays and dictionaries, you know, that if the interface the user used was identical for them, you know, it reduced the cognitive load on the user. I find that, you know, when I have to write a for loop, I'm reading someone else's code, and I'm reading, you know, 4x in D or something. I have to know whether D is I have to sort of figure out whether D is an array or a dictionary, and just figure out whether the thing you're iterating is a pair or not a pair, or things like that. Okay, so if the interface is 100% identical, then you and you have access to all these powerful functions like broadcasting, you know, you can write less code, do more with less code. The code's easier to read. It's fewer bugs because you're not rewriting things, and it has the opportunity to execute fast because we can work on the underlying implementation. Okay. The other thing we do here is we're using collections with well-defined order by default rather than the randomized kind of hash order that you get with dict and set. Okay, so you can round trip your data and it comes back in the same order and things like this. So let's look at how this is implemented. How does it all work? Okay, so the one big super type here is abstract dictionary. It has a type of key I and an L type T. And the main difference that you'll see between abstract dictionary and abstract dict is this. Okay, we know that abstract arrays iterate values of type T, but abstract dictionaries iterate key value pairs of type pair IT. So abstract dictionary will just iterate values of type T like arrays. Okay, so it's more array-like. We're not taking arrays and making them behave more like dictionaries. We're taking dictionaries and making them behave more like arrays. Okay. Now, just this one thing makes a few things a lot easier. It's easier to define behavior like map and broadcast, because if you're mapping values, you know that the keys aren't changing, they're identical. If you're mapping key value pairs and you're returning the key value pairs, those keys might have changed, and those keys might collide, and you have to figure out what to do when the keys collide, and what's the semantics of that. You know, do you throw an error? Do you merge them somehow? Do you keep the first? Do you keep the last? And if you're preserving the keys, you actually don't need to do all this hashing. You don't need to create new hash maps, hash tables. When the keys are identical, you can reuse the old data. So it's obvious how to make some operations really fast. It's also possible to copy and paste array code and just have it work out of the box, which is kind of beautiful. So the indexing iteration interface that I'm talking about, this common interface, is just simply that, you know, keys and values that iterate in the same order. You know, if you look at the first value of a dict through iterate, well, that's just indexing the dict with its first key. I mean, I would think that's pretty obvious thing to say. Just please note that currently, as it stands, it's not quite true for abstract dict, because first of dict will return a pair. You know, and there are some other objects which you know, there's a lot of interesting indexing behavior, for example, in a data frame, but less so for the iteration and so on. So you know, I think if you have simple rules like this, you can build upon them, and you can build semantics of functions like map and broadcast and everything really easily. The indexing iteration here, indexing interface here is based around keys. So if you have an indexable container or keys on it, it gives you a collection which is, you know, full of distinct things, because the keys have to be unique. So it behaves like a set. Okay. Arrays have keys, and when you do the keys of a vector, for example, you get a unit range back. So if you have a 3-element vector, you get the unit range 1 to 3 back, more or less. So 1 to 3 is itself an abstract array. Unit ranges are abstract arrays. Okay. It can iterate, it can index like an array. And it has a special property that when you do index the keys in an array, you get the key back. Okay? When you iterate 1 to 3, when you index 1 to 3 with the number 2, you get the number 2 back. And the same property holds if it's a Cartesian index. It's a high dimensional array. You get exactly the same thing with Cartesian indices. If it's an offset array, you get exactly the same thing with the indices of an offset array. Okay, even if the array doesn't start at index 1, you still have that property that when you index the keys, you get the key back. Okay, so what we have here, we don't just define abstract dictionary, we define another supertype, another abstract supertype called abstract indices, which the keys of a dictionary must return an abstract indices. So the abstract indices themselves are a type of abstract dictionary. Okay, and you know, it has sort of the key type I, and the dictionary it corresponds to has a key type and a value type of I, right? Because you can index these things. You can index the indices with I and get I back. You can iterate it, and when you iterate it, you get the value type back, and the value type is I because it's the same as the key type, because you want to iterate the elements of this set, right? So this relationship above, I've shown this to people before, and some people have been quite surprised. It's like, hang on, we're dealing with sets. Why do we need indexing for sets? Why do we need this weird rule for dealing with sets? Well, you can still do all your set stuff, but we can do more things, right? So it's only adding, okay? And so don't be afraid of it. And basically, you have to have this behavior if you believe two things: that dictionaries iterate values, and that the keys of dictionaries also are dictionary. So if you have just those two things, you must have this relationship above. Okay, so don't worry if it seems a bit strange. We'll find out that it's quite powerful. Okay, so that's at the abstract level. Let's look at how it's implemented at the concrete level. So the default hash indices, it's quite similar to the default dictionary set in Julia. It's a hash table, but it has an extra layer of indirection to make it ordered, just like in orderedcollections.jl. Okay, so let's say you want to find, you want to ask the question: is an element in the set? Is I in indices? Okay, if with a normal hash table, normal hash index, what you do is you hash I, you get some number, you take the modulo with the length of the hash table. So the more elements are, the longer that has to be. And then you get an index, and you look at that index. So let's say this returns 3, you look at I3. There might be other i's which hash to the similar value, modulo 8. We have to double check whether it is in fact the correct I, or it's not one of these other i's. And if yes, then yes, it's in the hash set. If no, we check the next one. We do something called linear probing, because it might just have been bumped to the next one. So that's either yes or no. And eventually we might linear probe until we hit an empty slot, and then we can say, oh no, it's definitely not in the set. Okay, so this is how you check whether something's in a hash map. If you've never seen a hash map before, sorry, it's probably a bit brief, but yeah, we don't really want to dwell on this. With an ordered hash index, you actually have an extra layer of indirection. You have the hash table itself contains just indexes into a more compact array, which contains the i's themselves. So the blue array now has less empty slots, and you find out which element of the blue array you are by looking up the hash table, and the order that the i's are in now can be whatever you choose. It doesn't depend on the hash anymore. So for example, in this case, we default to insertion order. It's the first thing you insert is the first element, the second thing you insert is the second, and so on. And you know, if you do linear probing, you might sort of be jumping around following these pointers. Okay, so with the dictionary, we're doing something really interesting. We're defining the dictionary as the composition of indices and a values vector. Okay, so if you have a look at the bottom, in a standard hash dictionary, you have a hash table, and you sort of replicate that array for the values. So that the indices and the values sort of share common indices. But in the ordered hash dictionary, actually, the values vector is actually shorter. It's only the length of the number of values that you have. Okay, so if you think we have all this extra indirection, we might be using more RAM. You can actually be wrong. You can actually use less RAM on the right if there's if the value in the index type size is large, and the number of slots, empty slots, is large. Then you actually save RAM on the right. So it's a bit of a trade-off. The other thing I'd like to point out here is most languages I've come across, including Julia, model their sets as containing dictionaries with a value type of null or nothing or nil or unit, and do it the other way around. Okay, so here I've sort of twisted the usual thing inside out, so that you can have many dictionaries that share the same indices. Okay, so for analytics style problems where you know lots of different data sets might be indexed by the same thing, you can actually save a lot of effort and RAM by just reusing the same index over and over. So for example, the blue and the yellow vectors on the right could be reused in multiple dictionaries. Okay, so the performance here, well, because of the extra indirection, the lookup, insertion, deletion can be slightly slower. So in the implementation, sometimes it's faster, sometimes it's slower than set and dict. Okay, but iteration itself is massively faster. Okay, so just like we saw in ordered collections, just like we saw over 6 years ago when trying to implement similar things in base, we discovered that iterating over these dense vectors is much faster than trying to iterate through the sparse hash table values. Okay, and that's it. And we also can be a little bit more clever now with this extra layer of indirection. We can do a lot of things with this hash map without dealing with any hashing, without hashing any values. Okay, I may have misattributed this quote. I'm not sure. For example, if we had this problem, we wanted to transform the values of a dictionary with 10,000 elements, how many hashes must I compute? So I think the easiest way that I know of implementing this in base dict is using a generator. It's probably the most readable and easiest way to write this kind of thing down. So you create a new dictionary from the pair K of f of v from an old dictionary which contained pairs KV. Okay, it's not too bad, but every time you insert one of these new elements, it has to rehash K, find the part in the hash table that we're going to store it, and put it there. Okay, so there's hashing going on. But with map f of dict in Dictionaries.jl, you don't have to do any hashing, because all we need to do is perform the map over the values vector. The indices are preserved. We don't care about what's going on in the blue array and the yellow array. Okay, it's sort of irrelevant. And you could map over the blue array and create a new value array as well. Okay, so the secret sauce here is tokens. We're not actually implementing this in terms of these underlying arrays. There's an extra layer of interface which means that anyone can go ahead and implement a performant dictionary that is as fast as it can be, and can share indices and can share tokens and all these sorts of things. So a token is something that lets you find an element in a dictionary. Okay, so rather than working as I said, with a concrete implementation of how to make things fast for dictionary and other dictionary types that are in Dictionaries.jl and dictionary types that you have to write yourself, we have these tokens. So a token is a thing which lets you get something from the dictionary. In the example of the hash table, the token, if you do all the hashing and the is equaling and so on, and you figure out which slot number the value is in, then that is the token. So for example, I is stored in slot 4, and get token of indices i's is 4. Okay, and then when we want to get the value in the 4th slot, it's just a get index and array. It's really fast. Okay, and if we wanted to find the 4th value in a dictionary, it'd be really fast. So what we have here is we kind of have two interfaces. We have a standard interface for users. It looks a lot like what's in base. It shares a lot of functions with array and dict that we use currently. And then on the right we have this developer-focused token interface. So if you want to create your own generic functions, or if you want to create your own new implementation of a dictionary, you're going to be either using or creating these functions on the right. Okay, so everything goes through tokens. You get a token, then you get the value, or you set the value, or something like that. If you look at this table's partitioned into 3 sections, so there's traits for telling you whether a dictionary is settable, so can you set the values or not, or is it immutable, or if it's insertable, can you create new keys or delete keys. Okay, so with the insertable interface, we've done something a little bit different to what's in dict. There's explicit functions for creating new keys for insert, whereas setIndex will only override an existing value that has an existing key. Okay, so we're not confusing our insertion and update commands. There's an upsert operation called set, and then you have delete and unset, which are like the opposite of insert and set. But if you wanted to create your own dictionary, all you'd have to do is implement the functions on the right. These traits, define these traits as appropriate, and also define keys. You must define keys. If you do that, you get all the fast mapping and filtering and everything that you have in Dictionaries.jl. For example, a really simple example, if you're just looking at getIndex, getIndex is actually defined internally in terms of getToken and getToken value, right? So it's pretty simple. Yeah, and it allows bounds checking and things like that, inbounds annotations and stuff like that, so we can make it fast. So what I'm going to do in this last section of this talk is we're going to switch over to the REPL. I'm going to look at a few different things you can do with it, just so you get a flavor of using this package, and hopefully maybe you can see some of its conveniences. So here what I've done is I've got a new REPL open. We're using dictionaries. It's easy to install. We just add dictionaries, and we're going to define a new set. Okay, so in this set, it's an indices set. It's not a base set, and it's just a set of characters A, B, C. And in a set, you could just ask, is something in the set? Is something else in the set? And you get true or false back. Okay, so it's basically the sorts of things you can do with sets. This is this magical indexing operation that if you're just thinking of sets, you'd never probably normally want to do. But if you're treating this thing like a dictionary, you will use it quite often, and we'll see that this being used a bit later on. If we try and index it with something that doesn't exist in the set, we get an index error, okay, like a bounds error, but for dictionaries. If we wanted to insert things into the set, we can insert things with the insert function. We can delete things and so on. Okay, so that's basically how it works. If we want to sort of start doing more interesting things with them, I'll switch over to just sets of integers, because we can do addition and different algebra with it. So we have this ins 1, 2, 3. Okay, so and we can do things to it. We can filter it. Now filtering is not too surprising. We can look for all the even things in the set. We could look for all the even values in a dictionary as well. It works the same for dictionaries. And there's this function filter view. So this lets us do a lazy filtering. So it just contains the predicate and the original collection. And then as you iterate it or whatever you want to index it, it will check whether the filter predicate's true or false, sort of dynamically. So this means you could do filter view on a very, very large collection of things, and defer the calculation of the filter later on rather than reallocating. Okay. You can do reductions. So for example, you can sum the indices. That's not too surprising. But what is surprising is that when you compare the speed of this to the base set, it's actually massively different. So you'll see it's 37 microseconds to sum up 100,000 integers in indices. If we try and do the same thing in set, it gives you the same answer. However, unfortunately, it takes approximately 20 times longer to do exactly the same computation. So this is just partly due to the fact that these ordered sets and ordered dictionaries, they're much faster to iterate through the values and indice values than it is to go through the hash map and worry about all the empty slots and worry about that as you go. Also, there's a few things I've done to make it more efficient, but yeah, pretty much you're getting behavior which is getting closer to array. In some cases the same as array depending on the operation. Like the map operation. So the map operation is actually really interesting. So let's map through the identity function. If we map through identity function, you get the same value back. So the values of an indices is the index. So this returns a dictionary where you've just basically copied the indices and the values. If you map it through isEven, you get to see which indices are even and which indices are odd. Okay, with the false, true, false. One is a false number, two is a true, one is a odd number, two is a even number. Okay, broadcasting. I love broadcasting. Everyone loves broadcasting. You can see that the keys of this dictionary, they are exactly as I said before. They're equal to the indices themselves, so we're not making copies of all these hash tables, and we can do all kinds of broadcasting like we'd normally love to do. Okay, and we can set index and stuff like that. This thing is mutable, right? And you can insert elements and delete elements and things. The similar function, it will copy it'll create a new values array with undefined values inside of it, and then you can start filling them up with whatever algorithm you like. Okay, so the next thing I'd just like to quickly talk about is the idea of grouping. Grouping is a powerful operation. This is defined in splitter by combine, which has a bunch of data manipulation operations. So let's take the numbers 1 to 10, and we want to put them into two groups, a group of the even numbers and a group of the odd numbers. Okay, so if we want to look at that, we could create a dictionary with false and true for the even and odd numbers, odd and even numbers, and we can, for example, extract the even set or the even numbers, just like that. Okay, so the group operation. This thing is a dictionary. When I created this thing, what I immediately wanted to do is I wanted to do things with the groups. For each of the groups, I wanted to add them up. I wanted to create their mean. I wanted to do some statistics or some transformation on each of the values. And when I did this, I couldn't do that when that was a base dict. Okay, this broadcast operation wasn't defined, and so this sort of spurred me to actually create this entire package. So the fact that we can easily take a dictionary of complex values and do a transformation of those values and return a new dictionary is really powerful. So we can add up the even numbers and the odd numbers, and you get those sums. If you want to do it faster, there are reductions, group reduce, group sum, group count, and so on, which do it without an intermediate allocation. And then the final thing in the last minute or so, I just want to talk about a new type of table. So in type tables, we've always had these array tables where each column is an array and it's presented to you as a struct of arrays. But here is my family, names, ages, and genders. If we have a look at this, there's these arbitrary numbers on the left. For example, if my wife was to create this table, she might swap rows 2 and 1. So they don't really have any meaning, these indices on the left. But what we do have is we have a primary key. We identify each other by name. I don't wake up in the morning and say, hello, number 3. I say, hello, David. Yeah, so this is a table with a primary key. You can get a column through its primary key, row, sorry. You can get a column and it returns a dictionary, which you can still index with the primary key. It's not an array, it's actually a dictionary. And and you can still do all the beautiful grouping operations. We can group my family by males and females, for example. In the future, I'd love to look at doing partition tables, like nested things, which work a bit like index tables. Tables with multiple primary key columns, and for these things we actually need to use multi-dimensional dictionaries. So that's really what's next on the list for me. So with this dict table thing, it's worth noting that we get all this almost for free. We've got this extra yellow hash table at the top compared to a normal type tables table, but the rest of the values are just as compact, just as efficient, just as fast to deal with. Okay. So you know, you're getting, I think, a lot of convenience by indexing your data with its primary key out of this with not much cost. So Dictionaries.jl, if you want to use it, it's easy to add, it's easy to use. You can find me on GitHub. I'd love to hear feedback, and thank you so much for listening.